For millennia, performing complex mathematics required the physical movement of objects. To model the motion of the stars, ancient Greek scholars relied on the precise interlocking bronze gears of the Antikythera mechanism. By the 19th century, inventors like Charles Babbage attempted to scale this architecture into industrial, steam-powered calculating engines made of brass and steel. But as long as calculation was bound to metal, the speed of information processing was strictly limited. Every logical operation was capped by the physical constraints of mass, inertia, and friction. The shift to wireless radio in the early 20th century allowed for instant global coordination, but it came with a fatal flaw. Because radio waves broadcast in every direction, any adversary with a receiver could intercept a nation's most sensitive communications. To secure their messages, the Axis powers engineered cryptographic machines like the Enigma. These devices used rotating electrical wheels to scramble letters into billions of incomprehensible permutations, making manual decryption effectively impossible. These machines created a mathematical wall. The Enigma alone offered 159 quintillion possible settings, a scale of complexity that human minds, working with pencil and paper, were too slow to ever unravel. To survive the intelligence war, Allied engineers needed a new class of machine, one capable of testing logical hypotheses faster than any moving physical part. This requirement led to a profound engineering realization. Abstract logic can be physically executed by electricity. A circuit can represent true when current flows through a closed switch, and false when it is stopped by an open one. Polish mathematicians created the Bomba. These blueprints show an architecture wiring Enigma replicas together, driven by one electric motor. The machine spun rapidly through combinations until electricity found a logical match, physically halting the gears on a decryption key. At Bletchley Park, mathematicians and engineers, including figures like Alan Turing and Gordon Welchman, scaled these electromechanical concepts into massive, high-speed decryption factories. These engines proved that physical circuits could evaluate truths and execute complex algorithms, literally computing through the movement of electricity and motion. As ciphers became more complex, these machines were forced to spin at blistering speeds. Brass rotors reached 850 revolutions per minute, pushing moving metal to its absolute mechanical limit. At these speeds, engineers hit the barrier of inertia. The spinning parts carried so much physical mass that when a mathematical solution was found, the machine could not stop instantly. It would blow right past the correct setting. To overcome this, American engineer Joseph Desch added electronic vacuum tubes to the machine's architecture. These tubes acted as an electronic memory, capturing the exact microsecond a solution occurred, so the mechanical gears could be rewound to the correct position. This hybrid design proved that while electricity was the future, mechanical computation was reaching its physical limit. To solve the most complex secrets of the war, the gears had to be removed entirely. The ultimate challenge arrived with the Lorenz cipher, a machine used for strategic communication between Hitler and his high command. It utilized 1.2 billion combinations, far beyond the capacity of any mechanical rotor system. The British initially tried attacking Lorenz with high-speed paper tapes, but the mechanical strain was too high. The tapes frequently stretched, tore, and melted under the friction of being read at high speeds. Engineer Tommy Flowers proposed a solution the academic establishment found impossible, discarding moving metal and relays in favor of thousands of silent vacuum tubes. The result was Colossus, processing 5,000 characters per second through the silent flow of electrons. Lacking moving metal arms or clattering relays, it was unbound by mechanical friction. By replacing gears with circuits, Colossus became the world's first programmable computer, crossing into the electronic age. When the war ended, the computing revolution was intentionally halted. To protect cryptographic secrets during the emerging Cold War, Winston Churchill ordered the systematic destruction of the Colossus machines. Engineers were ordered to burn their technical blueprints in furnaces. The physical evidence of their achievement was erased, and the pioneers of electronic computing were sworn to total secrecy for decades. Although the machines were gone, the discovery survived. The engineers and mathematicians who built them carried the knowledge into civilian life. certain that high-speed electronic logic was a reality. This knowledge led to the stored program architecture. Instead of manually rewiring machines with physical patch cables, software was stored internally in electronic memory, the same basic framework used by every computer today. This timeline illustrates the direct evolution of these components. This shows the path from the physical rotors and relays of the wartime bombs to the Williams-Kilburn tubes that enabled the first fully programmable memory systems. The mathematical methods used to break these ciphers, specifically the use of statistical analysis to reverse engineer logical structures from encrypted data, now form the basis of modern cybersecurity. The safeguards protecting the modern internet are built explicitly to thwart the same statistical attacks pioneered during the war. The necessity of survival forced the fusion of pure logic and physical engineering. From rooms filled with beers and vacuum tubes, the digital world was born.